Hi everybody, welcome back to another video on Feynman integration. Today I'm going to be doing something a little bit different. I'm going to actually be doing it out on the board instead of having it all written out beforehand. And we'll see how this goes. I'm going to leave it up unedited. So there's going to be probably a few mistakes and it might be a longer video. I don't know. Let's see. So anyway, the integral we're going to be solving is that. It's the integral from 0 to infinity of the arctangent of x minus the arctangent of 2x all over x dx. Going to be tough to solve that using traditional methods. So we're going to use Feynman integration. So the first thing we're going to do is we'll also call this f of t by putting a t in there. And that will make it a function of t. The reason I did that is because when you use Feynman integration, you take the partial derivative with respect to t of that integrand right there in order to get rid of that x. And you can see that will happen when you do that, because using the chain rule, you'll get the derivative with respect to t of tx, which will create an x on top to get rid of that x on the bottom, which is really kind of a pain in this problem. That x is a problem there. So we want to get rid of it. So we make a function of t that's equal to something very closely resembling our original integral, like that. Then what we do is we take the derivative with respect to t, like I just said. So first I want to note that if you evaluate f at the point 2, so f at the point 2, you'll get 0 because you'll just end up with arctangent 2x minus arctangent 2x, which will be 0. So that's going to be equal to 0. And originally what we had wanted, don't forget, is just tangent inverse x minus tangent inverse of 2x. So if we plug in 1, we get our original integral back. So we'll note that by saying that I is equal to f evaluated at the point 1. All right, now taking the derivative with respect to t, we get that f prime of t is equal to, okay, well, let's be careful. This whole second part is going to cancel out because it is a constant with respect to t. But we'll still be left with the integral from 0 to infinity. That part won't change. But then we have the derivative with respect to t of this right here. And again, if we take the derivative of the inner function, we're going to, this x is going to cancel out. So all we'll be left with is 1 over tx squared plus 1 dx, right? That's right, isn't it? That whole part will cancel out. Then you're left with 1 over this part squared plus 1 times the derivative with respect to t of tx, which will cancel out the x. Yeah, that's it. That's exactly what that is. Okay. So I'm going to be going through some of the steps actually involved in solving that. I'm not going to use just integral formulas. A lot of you would probably be able to tell me in your head what that is, but I'm actually going to walk through some of the steps of how I usually do it, because I'm not very good at remembering formulas. So a lot of times I have to figure these things out from scratch. So in order to do that, we're going to do trig sub. And usually when I'm doing trig sub is I like to create a triangle. We'll have the angle be theta. That's the pretty standard practice when doing trig sub. So now I would like to set up a triangle like this. I'm going to set up a triangle like this. We're going to have tx over here and 1 there. And then on this side, we'll have the square root of this squared plus this squared. You can see that's a valid triangle. Satisfies the Pythagorean theorem. So now we can see that based on this triangle, let's see, secant is this over this, hypotenuse over adjacent. So we know that secant squared theta is equal to 1 plus tx all squared. So that's true. We also know that the tangent of theta is equal to tx. I'd like to be able to directly solve for dx, so I will divide both sides by t. So now we have tangent theta over t is equal to x, meaning secant squared theta d theta all over t is equal to dx. Okay, so now I believe we have enough to rewrite that integral in terms of theta. Okay, so if our x is 0, okay, well let's do it step by step. We still have f prime of t being equal to something, some integral. If we plug in x equals 0, so we need tangent theta over t to equal 0, or tangent theta to equal 0. Tangent of 0 equals 0. So we'll have theta from 0 to, okay, now let's plug in infinity. If we plug in infinity for for x, we need tangent and then multiply both sides by t. So if we have x equals infinity, multiply both sides by t, we still have tangent theta equals infinity, and tangent pi over 2 is equal to infinity, I believe, yes, because pi over 2 would be here, and then it would be some positive value over some value that's approaching 0. You see, if you made theta equal to pi over 2, this would shrink to 0, and this would, stay some other non-zero value, which would make the entire thing approach infinity. I'm sorry. Yeah, it would approach infinity. So again, if we plug in infinity for x, we get tangent theta is equal to infinity. Tangent pi over 2 is equal to infinity. So theta is pi over 2. Now what's left? Well, we have 1 over this thing, which we just determined is secant squared theta. So we have 1 over secant squared theta times dx. dx is secant squared theta d theta over t. I'll bring that t outside. And then we have secant squared theta d theta cancel out. So we're really left with f prime of t being equal to 1 over t times d theta evaluated from 0 to pi over 2, which is going to be pi over 2t. Okay. So great, we have f prime of t. We're not interested in f prime of t, we want f of t. So to get back to f of t, all we have to do is integrate. So let's do that. Let's just cross out this whole middle step right here and just totally ignore it. F prime of t is equal to pi over 2t. We know that. So let's integrate both sides dt. And we know that that's going to give us, bringing the pi over 2 out and then integrating 1 over t dt, we will get pi natural log t over 2. So we have f prime of t. Make sure I'm not making any mistakes. Bring the pi over 2 out, then we'll just integral 1 over t dt. That's natural log t. So pi over 2 times the natural log of t. Yeah. Pi over 2 times the natural log of t. Oops, my mistake. F of t is equal to that, and of course, plus c. Can't forget about that. Yep, that's correct. Okay, so now we will utilize this. We'll utilize this fact right here to solve for c. Since f evaluated at the point 2 is equal to 0, we know that if we plug in 2 for our t, we get 0. So that would leave us with 0 being equal to pi over 2 times the natural log of 2, because we're plugging in 2 for t, plus c, giving us c being equal to negative pi over 2 times the natural log of 2. So I'll just directly write that right here. We solved for t, we solved for c, so now we can plug it in. Minus pi over 2 natural log of 2. So now we have our function of t defined purely in terms of t. And since we know that our answer is going to be equal to that when you plug in 1 for t, we know that I, which is f evaluated at 1, I is equal to this evaluated at 1. And you see, if you plug in 1 for t right here, this whole thing goes away because natural log 1 is 0. So we just have I being equal to negative pi over 2 times the natural log of 2. And that's it. I think that went pretty well. Assuming I got the answer right. I'm not going to post it if I didn't. I will definitely not post a wrong answer. But I'm pretty confident that that's the correct answer. So yeah, that's it. Integral from 0 to infinity of tangent inverse. I guess we started with tangent inverse x minus tangent inverse of 2x over x. And that's the answer. Hope you enjoyed that.